Delaware Tech, Chemistry 100, Chemistry 110, Acid and Base Equilibrium. So acids and bases, when they're in water, dissociate or associate with water or with each other, etc. And these reactions are all theoretically reversible reactions. So if I put a theoretical acid HA into water, it will break apart into H plus and A minus. Of course, we really know that what's happening is HA plus the water is reacting, and water is acting as a weak base because we're throwing acid in the water, and we will produce hydronium ion, the conjugate acid of water, and the anion left over from the acid, that would be the A minus, that's our conjugate base of our original acid. And so we keep in mind that whenever we see somebody write H plus, they really mean H3O plus hydronium ion. So for your purposes, I would stick with the second version of this, though I will tell you most chemists will use the simplified version shown above. Now, these are equilibria, except when you have strong acids, in which case it goes so far to the right that there really isn't any reaction going backwards. But we're going to talk about them as if they are all reversible for now. So acid equilibrium constant is a number. It's abbreviated Ka. It's called the acid dissociation constant, and it's a number that's associated with this equilibrium. And what you do is you take the concentrations of each of the products, and these brackets here, I'm going to label that over here. When you see a bracket around a formula, the bracket means concentration of. So in this case, it's concentration of HA. And HA is dissolved in the water, the acid is dissolved in the water, and a certain fraction of it will become H plus ions, and we'll have a certain concentration of that. And of course, when we just throw this in water, it will split. So whatever the concentration of H plus is, that'll be the same as the concentration of A minus, because they both came from one HA. Now, this HA in particular has only one proton. If I had two protons, then we'd have different concentrations for these. But you're going to keep that in mind when you're writing your equilibrium constant. And what you want to do is you're always dividing the concentration of each product divided by the concentration of each reactant after the reaction has come to an equilibrium. In other words, you throw it in, they settle, certain after a while the concentrations stay constant. That's the equilibrium constant. You measure those concentrations, and you take the concentration of the proton times the concentration of the anion divided by the concentration of the unreacted HA at the end of the reaction while it's in equilibrium. And so it's always the concentration of the products divided by the concentration of the reactants, and you always multiply them by each other. If I have more than one product, you put the other products in there and you keep multiplying. If I had more than one reactant, we would multiply these as well. So be aware that that's how you create these. How you create these expressions for an equilibrium constant. And this equilibrium constants are abbreviated K. Sometimes you'll see KEQ. But since this is a special one for acids, we call it Ka. And it's referred to as the Ka of an acid. And you'll notice that what this ratio is telling us is that if we have a lot of these things, in other words, the acid mostly broke apart, and only a little bit of this, as you would find with a strong acid, because the vast majority would be this, and this number would be incredibly tiny. Well, if we're multiplying two large numbers by each other and dividing it by a very small number, we would end up with a very large number for strong acids. So strong acids have very high Kas. Weak acids would have very low Kas, because in that case, this value would be very high, and the top values, the numerator values, would be very low, and we'd end up with a very low number for weak acids. But we have this equilibrium expression, and this is written based on this first simplified version. But what if we want to write it in the more proper way, which is what you need to do for this course? Well, you would write it as the concentration of each of the products multiplied by each other, so it's the product of the product concentrations, divided by the product of the reactant concentrations. So we have two products. Instead of a proton, we're writing it as a hydronium ion, which is really the same thing when it's in water. And we still have the other ions that we wrote, which look the same. So all of these are the same. The only difference is water. However, there's a very important rule whenever you're writing equilibrium expressions. And that rule says never include liquids and solids, pure liquids and pure solids. We don't mean aqueous solutions. We're not talking about things dissolved in the liquid. We're talking about liquids themselves, like water. If we had zinc in the reaction, that would be a pure metal. We wouldn't count that either. And the reason you don't count these is because their concentration doesn't actually change during the course of the reaction. So we never count water because it's a pure liquid. We would never count any pure solids like metals that might be just sitting at the bottom of the solution. Anything not dissolved in water or anything that is water or another pure liquid, we do not count in these equilibrium expressions. So you notice we end up with an expression that looks almost exactly like the simplified version, except we've got hydronium ion instead of protons, and those are really the same thing anyway. So it's actually the exact same expression, just written in a different way. So this is the equilibrium constant for it. And strong acids dissociate completely, so the numbers on the top are very high, and more dissociation means more product, and therefore we have very large Kas. Sometimes these Kas can be extremely large. You can have strong acids that have Kas where you take the concentration of the products divided by the concentration of the reactants, and so much of it has gone to the right that we have Kas for certain strong acids that are 10 to the 20 power. That's 1 followed by 20 zeros. Enormous numbers. Whereas weak acids might be 10 to the minus 10, so that would be 0.0 with 9 zeros and then 1. So very, very tiny numbers with weak acids. So weak acids and strong acids have very different Ka values. So let's look at bases now. And you have the same situation. Bases will also react with water. The base will pluck a proton off of the water because water now is acting as a weak acid, and you'll get the conjugate acid of your original base, your protonated base, and water has now become its conjugate base, hydroxide, in the process. And you can write an equilibrium expression for this. And again, we have each of the product concentrations. The protonated base, the hydroxide on the top, and we have the original base, whatever's left after equilibrium. So we're not measuring what we throw in, we're measuring what's there after we let it sit for a few seconds. And the water. Now, of course, you already know the water doesn't get counted. No pure liquid or pure solid gets counted, and we're left with this equilibrium expression of the concentration of BH plus, or the protonated base, times the concentration of the hydroxide, divided by the concentration of the remaining base, is our equilibrium constant for base, which we call Kb. So it's another equilibrium constant, but it's a special one for bases. So we have a Ka, that's the special equilibrium constant for acids, and a Kb, the special equilibrium constant for bases. And so strong bases will also fully dissociate. You'll get this reaction going to completion in this case, and there'll be almost none of your original base on the bottom, so you end up with this incredibly tiny number on the bottom and these huge numbers on the top, and as a result you get Kas that are extremely large in that case because of so many products. So strong bases have a large Kb, just like strong acids have a large Ka. So let's write a couple equilibrium expressions here and think about this. So we're going to talk about both the chemical reaction and the mathematical formula for the Ka or the Kb. So the first question says, write a chemical dissociation expression, so that's a chemistry expression, for nitrous acid, HNO2. Well, we know it has one proton, so we can write HNO2. You're always going to react it with water. So anytime you've got an acid or a base and there's no other added acid or base, you react it with water. And the acid will donate a proton to the water, so the water becomes hydronium ion, and what's left over is the conjugate base, nitrite in this case, and everything is dissolved in water except the water itself. So you would have this chemical expression, and of course if you wanted to write the equilibrium for that, the Ka would be the concentration of NO2 minus at equilibrium, the concentration of hydronium ion at equilibrium, divided by whatever acid is left over of this nitrous acid, and nitrous acid is a weak acid, so this number is not very large, and we leave the water out, and that would be our expression there. Now, if we wanted to write a mathematical expression for, say, another acid like H3PO4, this question asks, what's the mathematical formula for the first and second Ka of H3PO4, phosphoric acid? Phosphoric acid has 3 protons. It's a triprotic polyprotic acid, a triprotic acid. And therefore, we have 3 individual reactions that we could write one after the other. We could show one overall one that has all 3 protons coming off, but properly we would write them one at a time. So we would take one proton off at a time, starting with our phosphoric acid, and we react each time we're going to react it with water. So each one of these protons needs a water to bind to form a hydronium ion. So we take off the first proton, and that leaves behind a negative charge because we removed an H+. So remember, every time we're doing this switch, we're removing an H+ from our acid. And that will make our charge of our product more and more negative, and it will also take away one of the H's. And the equilibrium expression for this is shown here. This is called dihydrogen phosphate. It has a -1 charge. Our hydronium ion, another polyatomic ion that we learned about before, but is more important now that we're in acids, and the remaining phosphoric acid. But we can remove a second proton from this dihydrogen phosphate ion. It has 2 more protons to remove. We'll remove 1 more. So this will lose another proton. So now it will have a -2 charge and only 1 proton left. This is called hydrogen phosphate. And we would write our equilibrium expression as shown here. So notice what used to be on the top is now on the bottom because we're starting with that material. So be very, very careful when you're writing these expressions, and also notice that each time you're adding a new water. So we're going to need 3 waters by the time we're all done, and we'll produce 3 hydroniums by the time we're all done. Why? Because we're going to lose all 3 of these protons. So the third reaction is removing that last proton from hydrogen phosphate to make just plain old phosphate. And we need a 3rd water to do that, and we will make a 3rd hydronium, and the equilibrium expression for the 3rd Ka is phosphate concentration at equilibrium times hydronium ion concentration at equilibrium divided by the remaining hydrogen phosphate ion. So you'll notice in each case a lot of these things appear more than once in different expressions, so you have to be careful. But I will point out here, if you added all 3 of these reactions together, you'll notice we have 3 waters. We're making 3 of these, but we produced this and then used it up over here, so those cancel. And we produced this but used it up over here, so those cancel. So we're really just starting with this and ending with this. So our actual expression, I'm going to write it down here in our other question spot, is HPO4. This is our overall reaction. Overall, we've added 3 waters to this to get rid of all 3 protons, and this will be in equilibrium with our final phosphate, which has 3 negative charges on it now. Well, where did those 3 negative charges come from? Well, the fact that we made 3 positively charged hydronium ions from our 3 waters and our 3 protons. And that's our overall expression. And you'll notice if I write an equilibrium for that, an overall equilibrium, I will get the phosphate concentration times the hydronium ion concentration, but we have 3 hydronium ions, so I'd have to multiply it by itself 3 times, so we actually just cube it. It's easier to write that way. So it would be hydronium ion concentration times hydronium ion concentration times the hydronium ion concentration times the phosphate concentration, and it's much easier just to write hydronium ion concentration cubed. And on the bottom, we have our initial acid we started with, our phosphoric acid. Sorry about that handwriting there. And we don't need to write any of our waters, and that's our overall expression. And if you want to prove to yourself it's correct, you actually multiply each of these three together, and you would get this new expression here. And I won't do that here, but you'll notice if you have something on the top in one expression and something on the bottom, they're going to cancel. So all we're going to have left is this, our three hydronium ions, and what we started with right here in our expression. The others will cancel out. This will cancel with that. This will cancel with that. And we'll be left with this exact total expression here on the bottom. Now I'm going to have to erase this. I'll pause for just a second. You can pause the video and write this down if you'd like. Okay, I'm going to remove this now. Let's look at the last two expressions. These are relating to bases. One strong base, KOH, potassium hydroxide, and one weak base, ammonia. Well, the chemical expression for potassium hydroxide, again, you always start with the base and add water. If there's no other acid, water will do the trick. So KOH will react with water. The OH minus will steal a proton from the water, leaving an OH minus behind, which can bind to the K plus that you already had. And the OH minus, after it binds, will become the water here. So the OH minus, I may have said this wrong, the OH minus will become the water, and the water will become the OH minus again. And the K plus, the potassium ion, is kind of just there for the ride. It just goes wherever there's a negative charge to balance that charge. So the last one is write the Kb, the equilibrium constant for the base ammonia. So we first have to write out our chemical equation. Ammonia plus water makes ammonium ion. That's after it steals a proton from water. And hydroxide ion. Remember I told you that ammonia in water really is just ammonium hydroxide? But these are separate ions when they're in the water, so they can each be a product, and you look at the concentration of each of those, and you divide it by the concentration of whatever ammonia, unreacted ammonia, is still left in the water. And this is a weak base, so most of it still is in this form, in the bottom. And as a result, this number is very low, so you're always going to find a low equilibrium constant for weak acids or weak bases, and a high equilibrium constant for strong acids and strong bases. And with this, we'll stop here.